What is the difference between a classical bit and a qubit? Imagine a world where information isn't just black and white but can exist in a blend of both at the same time. That's what makes understanding classical bits and qubits so fascinating. Let's explore what sets them apart and why qubits are changing the game in quantum technology. A classical bit is the simplest piece of information used in everyday computers. It can only be in one of two states, 0 or 1. Think of a light switch that is either off or on. These bits are the building blocks of traditional computing, and they work in a straightforward, predictable way. When you press a button or click a mouse, you are changing bits from 0 to 1 or vice versa, and the computer processes this information step by step. Now, a qubit, or quantum bit, is a different story. Instead of just being 0 or 1, a qubit can be in a superposition of both states at the same time. Imagine spinning a coin on a table. While it spins, it's both heads and tails until it stops and you see 1. In quantum mechanics, this superposition allows qubits to hold multiple possibilities simultaneously. This means that a single qubit can representing both 0 and 1 at once, with certain probabilities, until measured. Superposition is what makes qubits so powerful. If you have one classical bit, it can only tell you one thing at a time. But with a qubit, you can encode many possibilities all at once. For example, two classical bits can representing for different states, but two qubits can representing all for states at the same time. With more qubits, the number of possible states grows exponentially, which is a huge advantage for solving complex problems. Entanglement is another key difference. Qubits can become entangled, meaning their states become linked no matter how far apart they are. If you measure one entangled qubit, it instantly affects the state of the other. This property has no equivalent in classical bits and is essential for quantum algorithms that can perform certain calculations much faster than classical computers. Physically, classical bits are made using electronic components like transistors on silicon chips. They are stable and easy to produce in large quantities. Qubits, however, requiring more delicate systems such as trapped ions, photons, or superconducting circuits. They often need to be kept at extremely low temperatures close to absolute zero to maintain their quantum state. When it comes to processing, classical computers use logic gates like AND, OR, and NOT to manipulate bits. These operations are deterministic and straightforward. Quantum computers, on the other hand, manipulate qubits with quantum gates that take advantage of superposition and entanglement. This allows quantum computers to perform certain tasks, like factoring large numbers or simulating molecules, much faster than classical computers. The amount of information stored in classical bits grows linearly. If you have 10 bits, you can store 10 pieces of binary data. But with qubits, the capacity grows exponentially. 10 qubits can representing over 1,000 different states at once, making quantum computers potentially powerful tools for solving specific problems that are impossible or take too long for classical computers. In summary, classical bits are simple, stable, and reliable, representing either 0 or 1. Qubits are more complex, capable of being in multiple states at once, and can become entangled with each other. These differences open up new possibilities in computing, cryptography, and understanding the universe at its most fundamental level. As research advances, the unique properties of qubits could lead to revolutionary changes in technology and science.